Chapter 3. Modern Quantum Mechanics. 3.1 Early History and Background. 3.1.1 History. The early phase of discovery for quantum mechanics moved into the modern quantum mechanics formalism with the discovery of Heisenberg of the successful application of matrix mechanics and the resultant uncertainty principle, 1925. In 1926, Schrodinger showed that the problem of finding a diagonal Hamiltonian matrix in the Heisenberg's mechanics is equivalent to finding wavefunction solutions to his wave equation. An interpretation of the wavefunction was then clarified in 1927 by Born. Dirac developed a manifestly relativistic formalism for the wavefunction and wave equation for fermionic matter, 1928. An axiomatic reformulation of quantum mechanics was then given by Dirac, 1930, laying the foundation for much of modern quantum notation and for critical issues such as self-adjointness. Dirac then described a formulation of a quantum propagation path, with quantum propagator having the familiar phase factor involving the action, in his paper The Lagrangian in Quantum Mechanics in 1933.
In a path integral description, the quantum mixture state, semi-classical physics, and classical trajectories are all given by the stationary phase-dominated component. A stationary phase solution that is dominated by a single path is typical for a classical system. Thus, variational methods are fundamental to analysis of physical systems, whether it be in the form of Lagrangian and Hamiltonian analysis, or in various equivalent integral formulations. Feynman's discovery of the path integral formalism wasn't solely based on the prior work of Dirac, 1933, although by appending that paper to his PhD thesis, 1942, its importance was clearly emphasized. Feynman also benefited from work going as far back as Laplace for selection process based on highly oscillatory integral constructions that self-select for their stationary phase component. This branch of mathematics eventually became associated with Laplace's method of steepest descents, then to the work of Stokes and Lord Kelvin, then to the work of Erdős, 1953.
Feynman and others then invented quantum field theory for electromagnetism, QED, during 1946 to 1949. More on this later. The extension to Electroweak occurred in 1959, and to QCD in 1973, and to the Standard Model in 1973 to 1975. Thus, the impact of the path integral revolution in quantum physics was felt well into the 1970s, but this was only the beginning. At their inception, path integrals were examined by Norbert Wiener, with the introduction of the Wiener integral, for solving problems in statistical mechanics in diffusion and Brownian motion. In the 1970s, this led to what is now known as the grand synthesis, which unified quantum field theory and statistical field theory of a fluctuating field near a second-order phase transition, and where use of renormalization group methods enabled significant advances from quantum field theory to be carried over to statistical field theory.
The grand synthesis is one of many instances to come where we see analytic continuation of a constant, or a parameter giving rise to familiar physics in the thermodynamic and statistical mechanics domains, showing a deeper connection. For further details, see Appendix D in Book 7. The Schrodinger equation, for example, can be seen to be a diffusion equation with an imaginary diffusion constant. Likewise, the path integral can be seen to be an analytic continuation of the method for summing up all possible random walks. 3.1.2 Background. Quantum measurement theory. We have a quantum observable that interacts with a classical apparatus to give a measurement. We suppose that a classical apparatus is the limiting case of a quantum process, and we require this limiting case to exist to have a complete formulation in terms of observable and apparatus. The existence of limiting cases, e.g., convergent sums, would occur in a theory that described a martingale process. In Book 7 we see that the fundamental evolutionary process is martingale, thus the quantum propagator formalism will have such limiting cases. Thus the existence of the quantum measurement theory formulation is guaranteed from the martingale convergence properties.
Canonical quantization shortcut. Let's go back to the 1920s and suppose that the fundamental matter description is a wavefunctional of some kind, as already indicated by early quantum mechanics, Bohr-Sommerfeld, the operative word being wave, and other than that we know that classical mechanics must somehow emerge. To be specific, let's consider the classical equation for the energy of a particle of mass m and momentum p moving in 1D in a potential v of x. See the equation. Let's now suppose that this equation is the characteristic equation that results from operation on a wavefunction with operators that yield the observed values. See the next equation, where E psi equals E psi, P psi equals P psi, and V of x of psi equals V of x psi. In the operator formalism and the wavefunction that it acts on, we thus have that classical variable that commuted before no longer do so now. Classically, we have.
See the equation. While x and p as operators, x and p operating on a wave function satisfy. See the next equation. Known as Dirac, canonical quantization on the canonical pair, x, p. Thus, if we now anachronistically jump to this single non-commutation feature, foundational in the later Dirac formulation, we have both his Schrodinger and Heisenberg formulations as well. For Schrodinger, consider that we can satisfy open bracket x, p close bracket equals IH over 2 pi if we choose an operator representation as follows. See the equation.
From which the Schrodinger equation results for our particle description above. From the canonical commutation relations, it is also possible to prove an uncertainty principle on those canonical variables, known as the Heisenberg uncertainty principle. Note, however, that given the assumption of an underlying wave theory, we could have presumed an uncertainty principle would exist on that basis alone, as established in the mathematics of wave theory, Benedict's theorem. From that required uncertainty relation on the operators of the quantized theory, we could have guessed non-commutation on canonical variables and shown consistency on such solutions, thereby arriving as the canonical commutation relations for operators of the theory merely from it being a wave theory. In what follows, we will see the utility of the Schrodinger approach to quantization by examining bound state configurations that exist for particles in a 1D potential well. Later, this approach is generalized to the 3D hydrogen atom to get the prior spectral results from early quantum mechanics. Eventually, however, we will want to examine non-bound state configurations, such as passing light through polarized screens in quantum state preparation experiments. In such descriptions, we shift from the wave function formulation to a wave function state vector representation, Dirac, or an operator or matrix representation, Heisenberg. For example, consider the following experiment with light.
Unpolarized light. Goes to, up polarized light. Goes to, diagonal polarized light. Goes to, sideways polarized light. In quantum mechanics, each filter action or measurement is vector space projective in nature. Later we will introduce projection operators, while classically, each filter action is selective in nature. Thus, classically, the sideways polarized light at the end has zero intensity, having been selectively filtered out at the first filter, passing only up polarization. Quantum mechanically, on the other hand, we project unpolarized through the up filter to get the up polarized light. We then project onto the diagonal filter to get diagonal polarized light. Inherent to this process is the underlying vector space mathematics, where the up polarized light can be written as a linear superposition of the diagonal and anti-diagonal polarized light, and the diagonal polarization is passed by the diagonal filter. The third filter for the quantum process then allows for 1/8 amplitude of the original unpolarized light to pass, instead of zero classically.
In Schrödinger's bound state solutions, we will see obvious reasons for quantized solutions due to boundary condition constraints. For the hydrogen-like atom solutions, this generates the .IC table. We will also see a perfect correspondence with the spectral results that drove the early quantum mechanics models, e.g. the Bohr-Sommerfeld model. To understand the projective nature of quantum mechanics, however, it is best to work in Dirac's Hilbert space formulation that will follow the Schrödinger examples. The Schrödinger, Heisenberg, and Dirac formulations are all equivalent in their areas of overlapping application, but for some problems some formulations are more suitable. For measurement theory problems like above, we could capture the projective aspect of the theory in the Schrödinger formulation using overlap integrals on the wavefunctions, but this is far more complicated than simply representing the wavefunctions as ket vectors, with projection simply accomplished by taking an inner product between ket vectors.